In the last video, we talked about the bulk properties of metals. In this video, we're going to talk about their atomic structure. The atoms within metals are organized into what we call crystal lattices. Now, I know that a lot of people think crystal and immediately imagine minerals and gemstones and species which are ionic compounds. But from a chemical perspective, a crystal lattice is any material in which the atoms are regularly organized. They're organized in repeating patterns of the same units, and metals fall into this category. You see some pictures in front of you of different ways in which atoms could be arranged in metals. Each of these is referred to as a unit cell. A unit cell is that repeating unit so that you have the ongoing symmetry that is observed within a metal structure. And yes, will also be observed in the structures of ionic compounds. So for something to be a unit cell, it has to repeat perfectly and without gaps. So I cannot, for example, have a group of circles, each of which I would call a unit cell, because while they do repeat perfectly, there's gaps in the middle, there's holes in the middle. So this is not a unit cell. If I'm looking at a picture, like for example, the one on the top left with the circles arranged in a regular pattern, and I want to find a unit cell in it, then I need to look for something that repeats perfectly, without anything getting offset, and without any gaps. And so what I'm drawing now, these squares that each have a quarter of a circle in each corner, that's a unit cell. That works. That's fine. It's not the only thing I could have done. Somebody might ask me, well, okay, but what if you just did a square with a circle in the middle of each? Would that be okay? Sure, that's absolutely okay. We're going to deal with my limited artistic ability here, but these could also all be unit cells, and a chemist can choose which unit cell they want to work with if they think that one is more convenient than the other. One could also imagine parallelogram-based unit cells for this particular picture. So one could also do something like this, and one could say, well, these are also unit cells, except that my picture isn't very well set up to show that, but these work too. Those are all unit cells. In each case, we've taken one picture and we've slid it along, and we've slid it along, and we've slid it along, and there's no gaps, and we're repeating it perfectly. And that's what a unit cell is. And a crystal lattice, a metal lattice, any other lattice is made up of repeating unit cells. What does that mean? Well, it means that this is not okay as a repeating unit cell because they're not all identical. Some of them have the black circle in the top right corner. Some of them have the black circle in the top left corner. If the unit cells aren't identical, they're not unit cells. So that's no good. So if I wanted to draw unit cells for this picture at the top right, I might have to do something like this, where I make a square with a quarter of a black circle in each corner and a white circle in the middle. And I could, of course, have chosen to put my white circles at the corner and my black circle in the middle as well. And I could have done something parallelogram based as well, as long as I've got identical repeating units. So pause the video, see what you can do with the bottom two pictures, see if you can come up with a set of repeating unit cells for each of those, and then once you've done that, unpause and continue with the video. So for the bottom left picture, we could, of course, simply imagine taking this picture at the top right and tipping it 45 degrees on its side and saying, well, really, that's just a square with the other square in the middle, and essentially build ourselves some diamonds. That would be perfectly acceptable. If we wanted to instead connect together the white circles with a black circle in the middle of each, and again, these are repeating along this direction perfectly, then we could do that. That would work fine too. Or if we wanted something that repeated left to right, we could go with a parallelogram-based approach. And again, we would wind up with something that was repeating perfectly without any gaps. Also note that you're not allowed to spin around your unit cells. You can't go triangle, triangle the other way, triangle, triangle the other way. That's not allowed. That is also not a unit cell. And the picture on the bottom right is just the picture on the bottom left without the little white circles. So again, we could either go with a parallelogram-based set of unit cells, or we could do the diamonds, like so. A crystal is going to have a lot of different unit cells in it. The smallest possible one is referred to as the primitive unit cell. Somebody could come along and say, well, you know what, Susan? Those two giant units there, they repeat as well. And yes, they do. And yes, you could choose to use those as your unit cells. But those are not primitive unit cells because they are not the smallest possible unit cell for that particular arrangement. So how do unit cells come about? Well, we have to look at how the atoms are going to arrange themselves within a material. And I think the easiest analogy to do is to imagine pouring a bunch of marbles into a box, and they spread out all across the bottom so that they're all touching. And if I look at the two pictures in front of me, one of which has a essentially square repeating cell, and one of which has one that's more along the lines of a parallelogram, which of those two patterns would you actually expect the marbles to naturally fall into? And if you said this one, you're right. The majority of the time, the marbles will arrange themselves to have the least amount of empty space because gravity is pulling everything down. And similarly, in a metal lattice, most of the time, the atoms will tend to arrange themselves to have the least amount of empty space. Not always. There are a few exceptions, as we'll see later. But it's very common to see what we call a closest packing type of arrangement, where the atoms are as tightly packed as possible. Now, if you were going to pour a second layer of marbles into your box and they were going to sit on top of these marbles, where is the second layer of marbles going? Well, the second layer of marbles isn't going to sit perfectly and immediately on top of the first layer because that's where the bumps are up. Those marbles are going to fall down into the gaps. You're going to wind up with the marbles filling the gaps, sitting in the holes, the little divots created by the first layer of marbles. And again, that is also what happens to atoms in a metal lattice. The next layer of atoms goes into the little divots. Whether you want to call those valleys or divots or gaps, the holes. Now, so that you don't have to deal with my scribbles repeatedly, I've repeated these images on the next page, minus the clutter on the inside of the marbles. And what you can see in the picture on the right here is our first layer of atoms, which we'll call A. It's layer A. That'll be useful later on when we start talking about how the different layers are arranged. If I drop a second layer of atoms in on top of that, they go into the gaps. So that's now the blue circle. So now we have the red layer A on the bottom and the blue layer B sitting on top of it. Now what happens if we add a third layer of atoms? Well, now there are two different sets of gaps in layer B. One option is for row C, our next layer, to fill the gaps where we can see the little white spot that nothing has gone yet. So one option is to put our next layer just like so, and then we'll get a picture that looks like that. And if I was going to describe that, we have the red layer A, the blue layer B, and the yellow layer C. And none of those is lined up perfectly on top of any of the others. But there's another option. I could simply put my atoms back in these holes here that are sitting over top of where layer A was, in which case I would then still have those white gaps, and I would have a red layer A on the bottom, followed by a blue layer B, and the yellow is lined up exactly on top of the A, so it is also a layer A. And these are both valid ways in which the atoms can pack, and a lot of metals use each of these options. And so this top pattern here is referred to as cubic closest packed, abbreviated CCP. And many metals have their atoms in a cubic closest packed arrangement. The bottom one is referred to as hexagonal closest packed. And there are also a lot of metals whose atoms naturally arrange in a hexagonal closest packed arrangement. So looking at those pictures, the top one doesn't look cubic at all, and the bottom one doesn't really look all that hexagonal. So where do those names come from? Well, we're going to start with the hexagonal one because it's the easiest one to rationalize. Where's the hexagon in hexagonal closest packed? Well, the hexagon comes if you look at 6 of the red atoms with one more in the middle, you get a hexagonal shape. Now that is not a unit cell because the next one over, if we were to start packing hexagons like this, there's gaps. It's not a perfect continuous arrangement, but that's where the name hexagonal comes from. And if we were to take that hexagon and everything underneath it and tip it on its side, you would get this picture on the right. Now, the primitive unit cell here is not the hexagon. The primitive unit cell here is this nice little parallelogram here, which repeats consistently, continuously throughout the whole entire lattice. And on the three-dimensional picture, it would be a prism like so. Okay, so there's a hexagon in hexagonal closest packing, fair enough. As I noted before, this would be described as AB, 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 however many times you want to say AB packing. Where's the cube? Well, for the cube, we actually need 4 layers of our lattice. And we either need models in front of us or we need to be really good at 3D visualization. So what we do is we take one atom on the top, and then the triangle of 3 atoms immediately underneath it. So that's the blue row here. And then in the other direction, the triangle of red atoms underneath that. So that's that red row. And then there will be another yellow atom immediately at the bottom of that. And if you take that thing that kind of looks like a cross between a flower and a Star of David, and you extract that from your lattice like so, and then you tip it on its side like so, you can see that we do in fact get a cube. And this cube is the unit cell. It's the repeating unit cell. It is shown with the atoms smaller so that you can see their relative arrangements and spaced out down here in the corner. And to see those layers again, here's your yellow one on the corner. Here is your layer of blue atoms. Here is your triangle of the 6 red atoms, and then here's your other yellow guy on the corner. And so we have here again the 3 alternating layers, the ABC pattern. And we have a repeating unit cell that is cubic in shape. Now, it's not just a cube with an atom on each of the corners. It's a cube with an atom in the middle of each face of the cube as well. And for that reason, it is often referred to as face-centered cubic. So face-centered cubic and cubic closest packed are exactly the same thing, different words for the same thing. There are, in fact, 3 types of cubic lattice. The face-centered cubic is the only one that is a closest packed one. It is also possible to have a repeating unit cell with just 1 extra atom in the middle of the cube or in the body of the cube, and that would be your body-centered cubic arrangement. And there is 1 metal that has a unit cell that is simple cubic, meaning 1 atom on each corner, and that's it. No extra atoms in the middles of the faces or in the middle of the cube itself. Be aware that these pictures are potentially a little misleading about how much of each atom is actually inside the unit cell, because you're seeing the complete sphere for the atom on each corner of the cube, but each atom on the corner of the cube only has a tiny fraction of it actually inside the cube. Each of these atoms on the corner is in fact in 8 different cubes. And so, therefore, only 1/8 of it is inside the cube and inside the unit cell. Similarly, these atoms on the face of the cube are in 2 different cubes, 1 on each side of that face, and so only 1/2 of each of those atoms is inside the unit cell. And so here is the periodic table of stuff for you to not memorize, simply showing you that there are a lot of elements that default to face-centered cubic or cubic closest packing arrangements, all those ones in orange. There are a lot of metals that default to hexagonal closest packing, all those elements in pink. There are a lot of elements that default to body-centered cubic packing, all those elements in blue. And then there's polonium. You don't need to know which element does which sort of packing. We just want you to know what the different types of packing look like and to have an understanding that metals do in fact organize themselves in lattices. So how do we know? How do we know what kind of lattice each of those metals organize itself into? And we can find that out using a technique called X-ray crystallography, which is useful for a lot more than just metals. It's useful for determining molecular structures of all sorts of different species and bonding structures of all sorts of different species. And essentially what you have to do is you have to grow a perfect crystal of a material, and then you pass X-rays through that material. And the material acts like a diffraction grating. It diffracts the wave function of the X-ray, and you get this pattern of dots that's detected by a detector, and then a lot of complicated math gets done to reverse engineer that diffraction pattern back to what did the diffraction grating have to look like? What did my structure have to look like? And it takes entire courses to learn how to do this, but it's an incredibly useful technique for people who want to know what the structure of something that they've made is.